So we started looking at the LNA, right? Design of the LNA yesterday. We kind of got somewhere. Let us see where this led us. So quick review. We realized that the probably the most obvious choice at the beginning is a common source amplifier for your LNA, because it has very high gain, right? Highest gain. It has an input voltage input, voltage output, highest gain, good input referred noise, and so on, right? So we decided to go ahead with that, but we noticed that the input is capacitive. So if the input is capacitive, the only way to match the input to 50 ohms, or actually I should not say the only way. There are several ways to match it. One of the ways is through something like this, right? Where you first tune out the capacitance using an inductance and then add another resistance to match the input to 50 ohms. Okay. Now, just remember that if you go to very, very small feature length processors, the gate resistance, the physical gate resistance of the device itself could be significant. Okay, so your input, which you thought was capacitive, could also have a real part, which means you will need to change this 50 ohms RS prime. You will need to change it appropriately. Okay, and the gain is GMRL by 2 if you have a resistive load, and you choose L by through this expression. Then we said, hey, you know what? You don't need L there. You can get even more gain by having an inductance. Okay. Now, the way I put it, LD resonates with CDB to give you this. Now, imagine CDB was very small. What would you do? You could either choose a really, really large inductor, which may be counterproductive, or there are several ways to go about it. Of course, you try to use a very large inductor, but once the inductor becomes very large, the area occupied, quality factor, frequency of operation, all these things come into play. So you can add your own physical capacitance, right? And that is very often done because you may want to tune the frequency of operation of the LNA, okay, over a much wider range than what you originally wanted. You may not want the frequency of operation to depend on the parasitic capacitance. You want it to depend on some fixed capacitance that you yourself know, that you yourself put in. Okay, there are various reasons for doing this. There is also a third way. A third way, if CDB was very small, its impedance was very small, its impedance was, since it's coming in parallel with 50 ohms, let us assume C was so small that 1 over j omega C is very large, so that most of your signal current ends up flowing into your load anyways. In which case, you can choose LD to be as large as possible. What is an inductor? We have discussed this in analog circuits 3002. When you added the series cap for a common source amplifier, you add an infinite cap here. What was this charged to? This was charged to VB. Remember that if you have an infinite cap, this is exactly the same as having a battery of value VB, right? Similarly, we also saw that if you establish a current I0 through an infinite inductor, this is exactly the same as having a current source of value I0. Okay, so what you could do, you could choose a large enough inductor such that at the frequency of interest, the impedance is so large that no current flows through it, so no signal current would flow through it. Okay, and all of the current would flow through the load. Such an inductor is called an RF choke. A choke is basically a very large inductor that acts as a current source. Okay, There is no, hopefully no signal current flowing through the choke. Signal current flows through some other path. Okay. To summarize, we have several options, but we will assume that you don't use a choke, you are going to resonate. Okay. So we will assume that the common source amplifier that you have chosen is resonating at the output and input. So this is kind of the final design that we came up with. RS prime and L is LD. Okay. And if you want to match the output, you will also do something else. Okay, you won't have CL, you want to drive 50 ohms, then you have to put in some 50 ohms and some capacitance. Okay. Yes. You should choose LSS. Yes, sure. So now, if you take CGS for example, it depends on length and width. Okay, GM well, which expression would be more intuitive? Since we have chosen here, maybe we'll take the one. I'll write it like this. If you have chosen VP for a particular value of current, some are not. So GM depends on W over L. Okay. So and your LNA requires a specific gain, which will depend on GM. So your W over L is fixed by the gain you require from your LNA. Whereas so if you were to choose a L which is larger than the minimum length, the W will also have to scale correspondingly for the same GM. Which means if you increase L, the capacitance CGS for example goes as L squared effective. Okay, so let me write it maybe in this form. Some alpha times L min. So, I'll write it as K to avoid any confusion. K is proportional to K squared. This is what I meant. Capacitive parasitics will start increasing faster compared to even if you, it will increase quadratically with the change in length, increase in from minimum length. Okay, this is what I mentioned yesterday. So you would want to use minimum length unless absolutely required otherwise. Okay, any other questions? Okay. Now assume that RDS is relatively large, or you have some parallel resistance RP. We saw that you will always have some effective parallel resistance RP. So the gain is given by this. So you basically have VGS which is equal to Vs by 2 if it is perfectly matched. Okay, the signal current is GM times Vs by 2. So the gain is for this circuit the gain is GM by 2 into RDS parallel RP. And LD resonates CL and CDP, L resonates CGS. Now there is a third capacitance which we have not considered here. CSB you don't have to worry about because it is from source to bulk, and both of them are grounded. There is a third capacitance which is an issue for you, because CGD in many modern submicron, very deep submicron processes can be as large as 30% of CGS. It can be quite large. Okay, I know that in analog circuits you always assume that CGS was the largest capacitance. That is true. CGD was only supposed to be the overlap capacitance. However, if you make the length smaller and smaller, okay, L overlap, the overlap length. So let's say this was the device. This was L overlap, okay, can become a significant fraction of L. Okay, so CGD can become a significant fraction of CGS, and it can be as large as 25-30% easily if you take like 65, 45 nanometer processors and so on. Why is this a problem for us? CGD, as you can see, depending on how you look at it, it is giving you either a feed forward or a feedback path. Okay, effectively you are going to cause instability in the device because the amplifier is no longer unilateral. If CGD were not there, everything looks great, but the minute you add CGD, there is a feedback path. Okay, and at some frequency the amplifier can become unstable. Okay, because if this LNA had very large gain, okay, you would have current flowing through that capacitance, which would depend on the output voltage. Okay, remember I told you folks that to brush up on S parameters long time ago. You folks said that you had studied it. If you were to look at this amplifier, you remember in the first couple of lectures I asked you folks, have you studied S parameters somewhere, and you folks said yes. Most of you said yes. Okay, if not, please, how many of you have not seen S parameters? Looks like several of you have not seen it. That's okay. So we will try to post a tutorial. I think I asked you folks to refresh your memories by going and watching a YouTube tutorial on S parameters. Is that correct? That's what I remember saying. Okay, if not, please do it now. Okay, as you can see, the assignment does have S parameters, right? If you, do you at least know what S parameters are? Have you studied S parameters in any course? Electromagnetics, transmission lines? You must have studied S. You cannot do transmission lines without S parameters. They didn't specifically say S parameters. You studied something called reflection coefficient? Okay, what else? You studied something called impedance matching using transmission lines. Voltage standing wave ratio. And what is the voltage standing wave ratio? Anybody remembers? Huh? Yes. I can't believe you can teach voltage standing wave ratios without knowing S parameters. If not, do you folks want me to teach a class on S parameters? Or will you be able to study by yourself? Huh? Okay, so maybe not today's class, I will go with this. Maybe in the next class. Okay, I will brief you on S parameters. Quick refresher on S parameters. For now, what I will tell you is that independent of what parameters you choose, note that because if you did not have CGD, the 1-2 parameter, whether you consider Z12, Y12, S12, whatever parameter, the 1-2 parameter tells you the effect on port 1 when you apply something on port 2. That will not exist. That will be 0 or infinity as the case may be, depending on what parameter you choose. Okay. Normally, if you apply anything to the output, there should not be any activity on the input. That's what makes it unilateral. The minute you do this, it is no longer unilateral. if you look at S parameters, S12 was supposed to be minus infinity dB. It was supposed to be 0 magnitude. It is not. It becomes significant. And you can actually relate that to stability. Okay. Now, we need to fix this. How do you fix this? Any ideas on how to fix this? Well, you can, if CGD was actually large enough, you can think about adding an inductor in parallel to resonate it out at your frequency of interest. That is one possibility. Okay, that will come with its own issues. The minute you put in an LGD, you are now DC shorting the gate and the drain. So your bias point changes now. You actually wanted some DGS at the gate and VDD at the drain. Okay, so what else? What other problems are there? Any other problems with this? Of course, CGD is, even though it's 30% of CGS, it's small, right? So now you can see that LGD will be like probably 3-4 times L, right? So maybe you might think, hey, you know what, let me add some fixed capacitance and then resonate it out. So now you can see you get into a loop of adding more and more circuitry to fix this. Okay. What are any other possibility you can think of to remove the effect of CGD? Huh? Incremental negative capacitance. Okay. How do you do this? Excellent. How do you do this? Instead of doing that, I'll give you a similar, this is a possibility, but I can extend this further. Okay. Instead of adding, of course, how do you generate negative capacitances? Somewhat? Okay, some materials operate in certain regions, that's great, but unfortunately we are limited by the CMOS process. You don't have those materials. So, of course, you'll now have to think of circuits to generate negative capacitance. How many of you did analog systems 2 semesters ago? You remember the gyrator, which was a generalized impedance converter? You can do that. Okay, you can use that to generate an incremental negative capacitance. Okay, what else? So maybe gyrator or gyrator based circuits maybe, but let me offer you an alternative. You can use Miller effect to create, correct, you can use Miller effect to create negative capacitances. Okay. In fact, one aspect I have not even talked about, but which will exist here, is the fact that VO by VI is very large. So already CGD will get reflected as a very, very large Miller capacitance at the gate node of the transistor. So the L required, earlier you were resonating out L with only CGS. Now you have to resonate out L with CGS in parallel with Miller effect of CGD, the Miller capacitance of CGD. Okay, please note that. So you can actually do something even better. So this is VO, this is VS by 2. So what you have here, okay, now if you were somehow able to inject a current equal in magnitude but opposite in direction to the output nodes and or the input nodes, okay, then you would negate the effect of this CGD. So the CGD is causing some, let us say, some current to flow like this. I gate drain like this. Where is that current coming from? Of course, it is going to come from these two paths, correct? It is going to flow into this and into CGS. But imagine I found out a way to let this current circulate and not flow from Vs and not flow into the transistors, right? That is indeed possible. How would you do that? I'm not talking about, I want to use positive capacitances only, no negative capacitance. So please note that if I were somehow able to add a CGD but connect this to minus VO, what will happen? So this current will now flow from here instead of flowing from Vs by 2. So this will go to 0. Okay. So such circuits, how do you create minus VO? If you had a differential circuit, if you already have ready access to minus VO. Okay, and it turns out that this technique is most useful when you have differential circuits. Okay, so this technique is called capacitive neutralization. Okay, your effect, removing the effect of the parasitic capacitance through another capacitance. Okay, if you do this, okay, you are, remember, CGD has one sign of feedback. By taking minus VO and connecting it like this, you are basically adding, if that were negative feedback, you are basically adding positive feedback or vice versa. Right? Just remember that. You are changing the sign of feedback for the other path. That is why it's neutralizing the effect. Of course, the third, probably the easiest way, which you folks will probably use in your exams, is to add a cascode transistor. Remember that a current control current source forces your circuit to be unilateral. It isolates the output from the input. So if I take some circuit and add a current control current source, input impedance is 0, output impedance is infinity. So effectively, even if something is happening here, nothing will get transmitted back to the input. Okay. So the easiest way, probably the most popular way, is to use a cascode. So even if you have CGD here, okay, anything happening at the output will not affect CGD, because by definition this circuit has a very high output impedance. Even if something happens at the output, very little incremental current will flow through the circuit, so very little incremental voltage should be generated here. Okay, in fact I can tell you that if these two transistors are identical, so let's call that Vx. What is Vx? In fact, so I'll write it maybe in specific in terms of this. Gm times Vi is the current flowing through M1. The impedance looking upwards should hopefully be 1 over Gm2. Okay, so it should be relatively small. Earlier the capacitance was going to VO, which was experiencing a very large swing because LNA has large gain. In this case, you don't have that. Additional advantage, Miller effect is reduced also. Okay. So this is a unilateral amplifier. And we will take this as the model for our circuits. In fact, if you don't add the cascode, because you have CGD, what will happen is that you change your input matching network, the output matching network, output matching, output impedance will change, and vice versa. Okay. Normally, whatever you do at the input of an amplifier will normally affect the output, always. If you change the input matching, the input impedance will change, the input signal voltage will change, the output signal voltage will change, and so on. That is what you want. If you start seeing the reverse, if you change the input match, if you change the output match and you see the input match changing, that's a problem for you. You want to, so you will find that the two resonances are coupled through CGT if you did not have the cascode transistor. Okay. So you have to neutralize, you have to unilateralize the amplifier before using it. Otherwise, one or more of two things will happen. First is that your input matching and output matching, simultaneous matching at input and output will become very difficult. Number two, the amplifier has a tendency to become unstable. More importantly, it may be perfectly stable at your frequency of operation. But remember that the amplifier needs to be unconditionally stable. It can still oscillate at some other frequency. Okay, and in fact that's what happens. Your op-amp based feedback circuits, if you remember, you may be designing them for operation from DC to let's say 1 megahertz. Okay, but the instability may be happening at 10 megahertz or 100 megahertz, right? So the op-amp will still oscillate at some high frequency and will be unusable. Make sense? Any questions? So now we'll start drawing everything with cascode amplifiers, and we'll ignore the effect of CGT because it is a second order effect. I'll show CL like this. Okay. Okay. So the gain of the circuit remains the same as before. It does not change. Okay. What is the noise figure of this circuit? Only calculated. Well, actually, wait. The gain does change slightly. Now that you have added a cascode, it is no longer RDS, it's R out, which is hopefully much larger than RDS. So now we will just approximate it to RP. Okay. Of course, please remember I am writing down the magnitude of the gain everywhere. There is a phase inversion. Okay. What is the noise figure? How do I calculate the noise figure of the circuit? Start from the fundamental definition. Total noise at the output divided by noise due to RS alone. Right? First of all, what kind of number do you folks expect? Huh? Not much larger than 1. Okay. 1.5. First thing I can tell you, let us assume that the transistors were noiseless. Let us assume that the cascode doesn't add any noise anyways. Right? That is for sure. If you were to write this. Unless the capacitance at the intermediate node, all of you are taking analog ICs also, I think. You know that unless there was capacitance at this node, right, the cascode will not add a lot of noise. Okay. So the noise sources are RP, is a physical resistor. It will add noise. M2 hopefully does not add too much noise. M1 adds noise. RS prime adds noise. And of course RS adds input source noise. Even if you assume that RP, M1, M2 are noiseless, what is the noise figure if they were all noiseless? M1, M2 and RP are noiseless. Please note that RS prime is still noisy. What is the noise figure? If everything else is noiseless. Yes, somebody. Everything is noiseless, right? So you just need to calculate the noise figure at the input of the transistor, M1. What is that noise there? You have two noise currents flowing into that node. One is from RS, the other is from RS prime. They are both equal. Correct? So if you had to calculate the noise figure, what do you think it will be? Noise factor will be 2. Noise figure will be 3 dB. This circuit can never have a noise figure lower than 3 dB. As you can see, it will probably be worse depending on how much the transistor adds. Okay? Actual noise figure is probably much worse. So let us now calculate the actual noise figure using this definition. So please calculate it. Can I give it to you as a class exercise now? Do you folks feel confident to calculate this right now? Okay, please do it now. Okay. No, not okay. So what is not okay? Okay. So 4 noise sources, 5 noise sources. Let's assume that this noise is going to circulate inside this. So let's ignore it for a moment. And looking at the short circuit noise current, this noise current will directly go through the short circuit. So that's the first term I have written down. IN1 square has 2 paths to its own radius or to 1 over Gm or N2. So it will go through 1 over Gm of N2 and it will go to the short circuit. So IN1 square will appear directly in the same. So up here look at the noise transfer function for INRS squared and INRS prime squared is exactly the same. Either one of these two currents, first of all, generates a voltage here by flowing into the parallel combination of RS and RS prime. You can assume that RS prime and RS have the same value because the LNA is input matched. If it is mismatched, you can find out the exact term also. But the effective resistance is RS by 2. Okay. So the voltage generated, squared voltage generated here, squared noise, is INRS squared times RS by 2 the whole square. This is RS squared by 4. That is this term here. That times Gm squared will give you the current flowing through the short circuit. So Gm squared RS squared by 4 times IN squared RS plus IN squared RS prime. Okay. So this is the total noise. I assume I ignore noise from N2. Make sense to everybody? I think by now from analog ICs we should come a second nature. What is the definition of noise figure? Total noise at the output. Does it matter whether it's voltage noise or current noise? Doesn't matter. Remember, okay, in our case we can take the total short circuit noise and divide it by the short circuit noise into the load. Okay. We also do it with voltage. As you can see, any impedance here will only scale all noise voltages by the square time. Okay, this is the same as the okay. So divide that over noise at the output due to RS alone, which is basically Gm1 square RS square that's 4 times. That's all. Okay. Please simplify this. Okay. Well, maybe I'll write it so that I don't skip a step. So in fact, remember that the magnitude of INRS squared is the same as the magnitude of INRS prime square. Okay, so these two powers are equal. So we'll actually get 2. Okay, that's what I wanted to point out. So you will get 2 plus, what is INRP square? 4 kT by RP delta F plus what is IN1 squared? IN1 delta F over INRS is what? By RS. Have I made a mistake? Oh, sorry, the IN, right? Not the input reference. Thank you. Yeah, of course. So now you see that the minimum noise figure is already 3 dB for this circuit. Okay. Huh? Why don't we include flicker noise? Because the assumption is that RF frequencies are in the hundreds of megahertz, if not gigahertz range. Normally, flicker noise operates from very, very, microhertz or millihertz to about, tens of megahertz. Okay. Okay, please simplify this. Just to make sure I'm also not making any mistakes. Over this is correct. I think this is correct. Please tell me if I've made an error. 4 by 3, sorry. Of course. Okay. So, of course, the usual stuff. What kind of intuition does this give you? Larger GM, right, means that your input referred noise is smaller and smaller. That makes sense for RP already, right? Because you are gaining up this current signal before it hits RP. So that makes sense for the first term. For the second term also it should make sense. If you were to refer the noise current of the transistor back as a voltage at in series with the gate, right? You know that goes as 1 over GM. Okay. So a larger GM will give you a lower input referred noise. So that should do better. Okay. What else does this tell you? RS you don't have a lot of control over, but RP you have control over. What this is telling you is that as RP gets larger and larger, the noise figure gets better and better. You should be trying to maximize the Q of the tank, LC tank circuit at the drain. Okay, that is what this is telling you. Its noise, if you maximize the Q, RP will start getting larger and larger. For an infinite Q, lossless LC tank, RP is infinity. Right? By definition, it produces no current noise. It's noiseless. An ideal LC tank is of course noiseless. Okay? So, I hope you have heard the usage of the term tank. Have you? If not, a resonant circuit is often called a tank circuit. This is just usual RF terminology, I assume. Okay, it's called a tank circuit. LC tank is the because it stores energy. Okay, I assume that is how the term, the word must have come about. Okay, apart from this, of course, maximize GM1. That also goes without saying. But even if you do all of this, fundamental minimum. this is a problem, because let me assure you, the noise figures you want from LNA should be like 1, 1.5, sometimes 2 dB and so on. 3 dB is just not going to cut it for most cases. Okay. Now, first question is, why is this 3 dB existing? Or why did it end up being 3 dB? Because you chose to add a resistance in shunt to match it to 50 ohms. Okay. Because the input of the transistor was capacitive. Okay. What this is telling you is that there is a bad way to go about this. You should not be adding a resistance to match to 50 ohms, because you know that all resistors add noise. Okay. Adding resistance to do input matching is a big no-no, because by adding resistance to do input matching, you are basically adding noise. Okay. But actually it doesn't matter, because assume that you didn't add resistance, the transistor itself had some parasitic resistance at the gate. Even if you match that through a matching network, it will produce the same amount of noise as a physical resistance of 50 ohms. I hope you understand what I'm saying. If you take a network, let us say resistors, capacitors, inductors. I think I mentioned this in passing. For example, okay, so maybe I'll just mention it now. Maybe it passed by too quickly. Let us say network had something here. It had some output resistance. This is an RLC network. Okay, maybe even a network of resistors R, doesn't matter. Okay, if it had some R out. In fact, you would replace the network across nodes N1 and N2 using a Thevenin equivalent. That is, Thevenin equivalent is equal to the output resistance, right? Is a Thevenin resistance. You can show that if you have a linear network, okay, the noise produced at output port is equal to the noise generated by an equivalent resistance or out. I hope you understand what I'm saying. The noise produced by this network N, okay, across N1 and N2, okay, is equal to the noise produced by the Thevenin resistance. Okay. So it turns out that noise also scales. If you use passive networks or circuits, that's a new word, circuits. So if you produce use passive networks to magnify or reduce impedances, of course voltages will also scale. The matching network actually scales voltages. It's like a transformer. Okay. It turns out that noise will also scale accordingly. Okay. You cannot get an improvement in signal to noise ratio. So if you had some parasitic resistance, let us say the gate resistance of the MOSFET, you use that to use the matching network to match that up to 50 ohms. Guess what? That is going to look like a noisy resistor of 50 ohms. Okay. So our problem is we need to find out a way to create an input impedance, okay, of 50 ohms while not using a 50 ohm resistance at the input. Okay, so that's our job for the next couple of classes. Okay, there are also a couple of other things we need to learn. For example, noise factor of passive lossy networks, as well as noise of a MOSFET itself. We have been assuming 8 KT by 3 GM. Okay, some slight modifications. We'll do that in the next class.